All right, my mighty remoters, I'm going to kind of go over part of this with you, and then you're going to do part of it on your own, and you're going to check it. This is what you're going to miss in class today. So it is about the second derivative, and the second derivative literally is just the derivative of the first derivative. So if I have a function, I take its derivative, it's its own function. The derivative is a function. And then if I take the derivative of that, we call that the second derivative. And we use this little notation and put two little tick marks up here to reference second derivative, or f double prime of x. And again, the derivative and then the second derivative will both tell us a lot about our parent function, the original function. So we're going to start with a fifth degree polynomial, and just in general, take a second and see if you can sketch what a fifth degree polynomial would look like in terms of number of terms it has at most, and how many times it changes direction. And then we'll talk about the maximum and the minimum, or what we call plural maxima minima. So take a second and see if you can come up with something. All right, so hopefully you paused it for a second, tried something. So if I have a fifth degree, and I'm just going to do x to the fifth, that means I have at most 4 terms. So I'm drawing all over my paper here. Again, you probably learned that last year or the year before. At most 4 terms, 1, 2, 3, 4. And then these points are called, this is a local maximum, and a local minimum, and a local maximum, and a local minimum. And I have more than one, so the plural of those are maxima, meaning more than one maximum, and minima. So you might see something about find the maxima or find the minima. It's talking about finding more than one. It might have more than one of them. Also, this portion is concave down to right there. Then this portion is concave up to right there. This portion is concave down to right there. And then it's concave up the rest of the way. So there's 1, 2, 3, 4 concavities. There's 4 mins and maxes. There are 4 turns, which are the mins and maxes. And because these little x's right here that I put on here are where I change concavity, those are called inflection points. And they are where I go from one concavity to another. Kind of like maxes and mins are where I go from increasing to decreasing, so I change my direction. So what we're going to do is we're going to just resketch that same graph. I'm going to kind of put a coordinate grid here, and I'm going to repeat that coordinate grid the whole way down. I'm going to try to carry down I'm not going to have actual coordinates, but I'm going to carry down as I work through each of these derivatives. So, and feel free to pause and work ahead and then check and see what you came up with is the same that I came up with. So the first thing I'm going to do is put my fifth degree polynomial on there. So I'm going to come up 1 turn, 2 turns, 3 turns, 4 turns, 5 turns. And it doesn't matter where my turns are or where I cross the x-axis. None of that matters. So the first thing we're supposed to do is on f of x, which is here, label the maxes and the mins with the letter m. So you could go through and do that. Actually, why don't you pause the video and go through and label all your maxes and mins with an M, and label your inflection points with the letter I. And again, that's where you're changing from concave up to concave down. So go ahead and do that. All right, I'm going to go back and show you. There's a max, a min, a max, a min. I'm going to put a little x and call that my inflection point. And these are approximate. You're not necessarily getting precisely where this is happening. And your graph looks different, so yours might be in slightly different places, but the number of them that you have should be the same. So notice that the concavity changes from negative to positive or vice versa. So this is concavity down or negative concavity, concave up, or positive concavity, concave down, concave up. So concavity changes at inflection points. That's a big deal. That's going to be something that's helpful. So inflection points. And the slope changes from positive to negative or vice versa at our maxima and minima. We already knew that. That's what we've been kind of focusing on as we've gone through stuff so far. So as I go up and increase and then turn down, decrease, that's where I have a max or a min. All right, so now what we're going to do is we're going to carry our graph down. And what we learned already is that anywhere there was a max or a min, I could come down here and it'd be a 0 on my derivative because the derivative is 0. It's a flat line. So here's another one. I'm going to come down and put a 0. This is another one. I'm going to come down and put a 0. And I'm going to come down and put a 0 here. So I have 4 maxima and minima. And so I have 4 x-intercepts on my derivative. And now my inflection points are going to come into play in a minute. So notice this graph is increasing. So these are all positive slopes. So on the left side of this, I have to have positive output. So that would be over here. And here, between here and here, they're all negative. So down here, they're all negative. But this is where the inflection point comes in. Where the inflection point happens is where I'm going to have a turn in my derivative. So bam. Now, do I know exactly how far up or down it is? No, but I do know it has to turn underneath because these are all negative slopes, so these are negative outputs. So this inflection point is going to be in between these two, and it's going to tell me that I'm going to turn and go back down. And then again, so these are all positive slopes, so these are all positive outputs on my derivative. And then there's another inflection point down here somewhere, and then I'm going to go like that. And notice this was x to the 5th. This is looking like an x to the 4th function. So x to the 5th, x to the 4th. And we have a couple things to fill in here. When the derivative is below the x-axis, f of x is decreasing. So this is kind of saying what I've been telling you backwards. When this is below the x-axis, my function up here is decreasing. And this is the opposite. If the derivative is above, then the function itself is increasing. So this is a place where the derivative is above, and that matches up to an increase in my function. All right, so hopefully you're jotting these down, because now I'm going to do the next one, and I'm going to have to bounce back and forth between these. But there's a max and min, so that's going to come down and be a 0. There's a max or min, that's going to be a 0. There's a max or min, that's a 0. On this one, it looks like I have a point of inflection right there, and another one right there, and that just is the way I drew it. That happened to be on the x-intercepts. They aren't necessarily going to be x-intercepts, but these are negative slopes, so I'm decreasing, which means my derivative has to start underneath here, and then this happens somewhere in between where I turn, and then there's another one down here, bam, and there's my second derivative, which looks mysteriously like a cubic. So here we have the zeros of the second derivative. So here's the zeros of my second derivative, 1, 2, 3, happen to be when the function, if I go all the way back up to the function and trace all the way up, those 3 zeros happen to correspond to these 3 values right here. So the 3 zeros on the second derivative happen to correspond to where f of x changes concavity. AKA, they are the inflection points. And when the second derivative is below the axis down here, then the first derivative is decreasing. So everything that was true about the derivative and the function is also true about the second derivative and the first derivative. So this is negative or below the x-axis. That corresponds to a decrease in my first derivative. And if, sorry, if the second derivative is below the x-axis, that means the second derivative is negative. That means the function itself will be concave down. So think about negative is corresponding to decreasing and concave down. And in contrast, if the second derivative is above the x-axis, then the first derivative happens to be increasing, and at the same time it would be concave up. So all these positive things are going on in terms of above. So think about it that way. So down here, what to think about in terms of the output of f of x is the height of f at x. The output of the derivative is the slope at x. And the second derivative tells you the concavity at x. And the concavity being, if the second derivative is positive, it's concave up, negative, it's concave down. All right, you're going to do a little bit of work here. So I first need you to adjust this a little bit. Because I didn't actually mean for that to flatten out. I want that curve to have a pronounced maximum there, not a mysterious is it or isn't it. This is a quartic polynomial, and this green one is a quintic polynomial, and this is intended to be flat. This comes down, flattens out, and keeps going down. So this is, watch out here. So I want you to pause the video, and I want you to try to do what we were doing. Make sure you label, like, this is F, this is going to be F prime, this is G, this is G prime. But you're going to do F all the way down to the very bottom. So you're going to keep going until you are at the last graph. So you just keep graphing derivatives. And I will tell you something I didn't note. After the third derivative, you don't use tick marks anymore. So actually it does say right at the top of your notes, thankfully. Once you're past the third derivative, you put a little 4 in parentheses and a 5 to indicate fourth or fifth derivative. So pause this thing, and then I'm going to share it with you. This might take you a few minutes, but that's okay. All right, assuming you've done the work and you've unpaused it, I could take a look. Mine is very, very sloppy, and I apologize for that. So just look at one column at a time. Notice as I go down the f of x quartic, it's quartic, it becomes cubic, it becomes quadratic. And once you get to quadratic, you guys have done a lot of those. Then that's a line, and then that's a constant slope, and it's downhill, so it would be a horizontal negative line. And then the slope of a horizontal line, talking about this guy right here, the slope of that is 0, so its derivative would just be 0, and graph 0 is a horizontal line at 0. So you kind of ran out of room. Now this one is where it gets a little bit tricky, because this point right here would have a horizontal tangent. So the derivative would be 0, boom, it's an x-intercept. But notice that I'm decreasing, and at that point, after that point, I continue to decrease. Therefore, the derivative has to stay below the x-axis for both sides of this. That's why it bounced. And it also bounces because this is concave up, switches to concave down. So when I turn concavity, I'm going to have, the derivative is going to have a max or a min. So that's why I bounced on there. So this one was a little bit tricky. The rest of this was kind of normal as it was before. That first one was a little tricky. All right, so then I went, again, I just kept going. Maxes and mins are zeros. Concavity, points of inflection are where my next derivative has maxes and mins, and I keep working my way down all the way, and I ran out of room. But one thing to point out that you need to know going forward is if you have a polynomial function, the derivative will also be a polynomial. Smooth, continuous, no asymptotes. Notice that as I went down, my degree, each derivative lost a degree, stopping at f of x equals 0 because there's no degrees to give anymore. And an interesting part is that as I go through my derivatives, the left-hand behavior stays the same. So, the right hand stays the same. They're all pointing down in the left column on the right side, and on the left side it goes from down to up, etc., etc. So your derivatives alternate on the left side, and behavior, the right side stays the same. All right, I'm running out of time, so I got to move along. I'm going to quickly set you up for the sine graph, and then you're going to do it. So sine graph, again, this would be pi and 2 pi, so that's like pi over 2 and 3 pi over 2, and the max of a sine graph is 1, the min is -1, and it starts at 0, and this may be some review for you, and it goes up to 1, it comes back down to 0, goes to -1, goes back up to 0, etc. So two things to keep in mind as you do the next phase, and that is that the slope right here, the slope of that point is equal to 1, and the slope right here, when you get to this point right here, that slope right there is equal to -1. Oops, that's a crazy -1, -1. So now your job is going to be to graph the derivative of sine below it, just like we were doing with the polynomials, and then take a look and keep doing it all the way down, and then we'll look at a pattern at the end. So do that, and then well, actually pause the video and take care of that. All right, so if you unpause and take a look, this is what your graph should have looked like. There's the sine is f of x, f prime, then f double prime, f triple prime, f quadruple prime. And if you'll notice that that first graph is sine and the last graph is also sine, you'll also notice that the second graph, the first derivative, is cosine. This is negative sine, it's just sine reflected, and this is just cosine reflected, so it's negative cosine. So if you didn't recognize the pattern on your own, now you know the pattern. I want you to think about tangent, what that would look like. And I also Would love to show you sometime how this derivative of sine and cosine business, it can